we start with a presentation of the Michael Penston Thesis Prize. And this will be given by Matt Nicholl, now of Harvard-Smithsonian Center for Astrophysics. The title is Unmasking the Power Source in Superluminous Supernovae. Welcome, Matt.
Thank you. Great. Okay. Thanks, everybody, for coming out, and thanks to the Royal Astronomical Society for inviting me to speak here today. I'm going to talk about superluminous supernovae, but before that, it's worth taking a moment just to review what we know about normal luminosity supernovae. So in a star about 8 times the mass of our Sun, or greater than that, the temperature and density in the core gets high enough that it can fuse elements all the way from hydrogen to iron. And once it makes an iron core, no more energy can be liberated from nuclear reactions. At that point, it takes more energy to fuse iron together than you get out of the reaction. So the core becomes unstable. And when it reaches a certain critical mass, about 1.4 solar masses, it collapses in itself to form a neutron star. And at this point, the outer layers of the star are violently ejected in a supernova explosion. So this synthesizes a large amount of radioactive material, primarily 56 nickel. And the decay of this to cobalt and then to iron powers a bright light curve that can reach 1 billion times the luminosity of our Sun. It stays bright for weeks or months. And in fact, we've been finding these supernovae for a very long time. They occur at a rate of about 1 per century in our Milky Way, and they are in the historical record going back to about AD 100. But in the last century, we've been doing a lot better than finding them at this kind of rate. With modern astronomy, we've been targeting massive nearby galaxies to essentially chase the star formation rate, look for places that form a lot of massive stars, and you expect to find a lot of supernovae. So that worked very well for quite a long time. But there's an inherent bias in this search strategy. So by looking at massive galaxies, you only find the kinds of supernovae that occur in those environments. What's been much more successful since around 2005, due primarily to technological advances, we've been able to survey the sky in a more unbiased, blind fashion. So with robotic telescopes and large CCDs, so for example, this is the CCD of the Pan-STARRS telescope here, you can survey the entire sky with no inherent bias for any particular galaxy type. And by doing this, we've actually found entirely new kinds of supernovae that occur in anonymous dwarf galaxies, like the galaxy you probably can't make out right there. But later you see a bright supernova that outshines its host galaxy. But the most interesting thing about these supernovae in dwarf galaxies is that many of them are actually superluminous. And what I mean by this is that they are more than 100 times brighter than any previously known type of core collapse supernova. As well as being much brighter, however, they are about 10,000 times less common. And it's this low volumetric rate combined with their preference for anonymous galaxies that means it's taken such a long time to find the brightest supernovae. So that seems kind of unintuitive. So the big question mark is what actually powers these incredibly luminous light curves. So there's our previous supernova. Here's a superluminous supernova. It's much brighter for much longer. And we really don't know why that would be. And that's the question I'm primarily interested in answering. But there are several other things that makes it really essential to study these superluminous supernovae. So as most of you are probably aware, in the last 10 or 20 years, people have used Type Ia supernovae to measure the expansion rate of the universe and shown that it's accelerating over time. With superluminous supernovae, you can detect them much further away and therefore probe the expansion of the universe at much earlier times. In a similar vein, because they're so luminous and detectable so far away, they're probably our most promising way for detecting the deaths of the first generation of stars to ever form in our universe, especially with upcoming surveys such as the James Webb Space Telescope. But before we can use them for these other interesting purposes, it really is essential to answer question number 1. How do you actually power these and what kind of stars do they come from? So as we find more and more of these unusual transients, 2 sort of broad categories have emerged. And these are typically referred to as Type 1 and Type 2. So what I've mostly worked on and what I'll be talking about today are the Type 1 superluminous supernovae. So these are events that do not show evidence of hydrogen in the spectrum. Instead, they show these very blue spectra that are dominated by oxygen-2 absorptions at around the time of supernova maximum light. There is also the Type 2 events, and these are the ones that do show hydrogen. And they look very different from the Type 1. Hydrogen typically shows up in the form of emission lines rather than absorption, and with a range of broad and narrow components. But those, I am afraid, I do not have time to talk about today. Okay, so the first question that you might reasonably ask is, if the superluminous supernovae are 100 times brighter than a normal core collapse supernova, perhaps they synthesize 100 times as much radioactive nickel. So in a normal core collapse supernova, explosive nucleosynthesis produces about 1/10 of a solar mass of nickel. So to power a superluminous supernova light curve, you would need about 10 solar masses of nickel, which is a huge amount to synthesize in this explosion. But there is one hypothetical model out there of a kind of star that would produce this much radioactive nickel, and that's what's called a pair instability supernova. So in this situation, you have a star that's 100 or 200 times the mass of our sun, and in this situation, this is just theoretical, the core temperature of the star becomes high enough that photons become unstable to electron-positron pair creation. So this removes radiation pressure support from the core, which then contracts, and it leads to a thermonuclear runaway that can synthesize a very large mass of heavy elements, including the required amount of 56 nickel. So in 2011 and 2012, the Pan-STARRS survey that I mentioned earlier actually detected 2 superluminous supernovae very shortly after the time of explosion. So if we look at the plot here, we can see the luminosity versus time. And these 2 events in black and blue, which are PTF12 DAM and PS111AP, we can see that they take about 50 days to reach their maximum brightness. And the timescale over which these things brighten is set primarily by the photon diffusion time. This is the time it takes for photons to actually escape from this ball of expanding matter that's been ejected by the supernova. And what we find is that for pair instability supernovae, all the predictions require this diffusion time to be at least 100 days, because you've got 100 solar masses of stuff to escape from. So finding these things early and measuring this rise time actually puts very strong constraints that rule out these nickel-powered pair instability models. And then since those discoveries a few years ago, we found much more of these events at early times and really started to pin down the timescales over which these things brighten and fade away again. And what we find is that there's a very large variety. So you can see some of the best observed examples here. You've got rise times between about 10 or 20 days and close to 50, 60 days. And we parameterize this here, and we see that, in fact, despite this diversity, the rise and decline scales actually seem quite closely correlated. And we can use these rise and decline timescales to measure the light curve width, and use that to put limits on the diffusion time and therefore the ejected mass. And we find actually that to generate any of these light curves, you really need ejected masses less than around 30 solar masses. So nowhere near this pair instability regime that I mentioned. And in fact, the objects from the previous plot are the ones I've circled up here. So these are probably the most massive events. Everything else is significantly less massive than that. So I think we can really say at this point that none of these objects really seem to be consistent with these very massive radioactive nickel-powered explosions. So before I discuss some mechanisms that perhaps can generate these light curves, it's worth taking a moment to think what we can learn from the spectroscopy. So the spectra I've plotted here are for probably the best observed superluminous supernova at this point, supernova 2015 BN. And I've just divided this up into early spectra in sort of blue and purple. These are spectra before the supernova reaches its maximum brightness, and later time spectra when the supernova is fading away again. And what we see is that at early times, the spectra are dominated by quite highly ionized species. So oxygen-2 and iron-3 are responsible for most of these lines. And the width of these lines gives a Doppler shifted velocity of around 10,000 kilometers per second. So this material is both very hot and very rapidly expanding. At later times, when the spectra cool, we still see sort of these metal line-dominated spectra. But we see lower ionization and more different species. So oxygen-1, iron-2, calcium, silica, and magnesium. But in none of these spectra, nor in any of these little zoom-ins I've done, do we see any evidence for hydrogen or helium. So it really seems like these are the explosions of stars that have totally lost their hydrogen and probably helium layers prior to explosion. So in fact, there's actually one type of normal luminosity core collapse supernova that also shares this property of having lost its hydrogen and helium layers before explosion. And this is known as a Type Ic supernova. So interestingly, it's been shown that by the time superluminous supernovae have cooled to temperatures comparable to normal luminosity supernovae, which takes a few months after explosion, the spectrum actually looks extremely similar. So in this plot, the bottom spectrum is an old superluminous supernova, and these are some young normal luminosity Type Ic supernovae. So in many ways, it seems like the superluminous supernova is like a normal Type Ic, but significantly hotter. And if we do a similar comparison of the light curves, we've got a template for Type Ic supernova here, and this blue regime is the light curves of observed superluminous supernovae. As well as being hotter and brighter, they also seem to be significantly broader. But the intrinsic shape is similar. So by applying a simple stretch to this, which is essentially saying we've got more ejected mass, we can map the normal type 1c onto the superluminous supernova. So it does seem to be a strong connection there, although we know the power source must be different because these are nickel-powered explosions. Okay, so how do we make a superluminous supernova? So we need the explosion of a massive star that's lost its hydrogen and helium envelope and some mechanism other than radioactive nickel decay to power the luminosity. We know from the spectra that we have a high temperature, and therefore the energy must be deposited once the material has expanded to a large radius. If the energy goes in too early, you lose the heat to adiabatic expansion. So there are two models that are pretty popular to try and explain this evolution that we see. So one is called generically the central engine model, but more specifically is usually thought of as what's called a millisecond magnetar. So in this scenario, the neutron star formed in the core collapse has both a very short spin period of a few milliseconds and a very high magnetic field. And in this case, you essentially have a magnetic dipole that acts as a battery that heats this material as it expands. And this is kind of similar to the engines in long gamma ray bursts, except that in a gamma ray burst, the energy goes in very quickly and essentially drives kinetic energy, whereas in this scenario, the time scale of the engine is well matched to the diffusion time of the ejecta. And in this situation, the energy actually diffuses out when the supernova has reached a large radius. The competing model is called the circumstellar interaction model. In this scenario, you have a supernova ejecta expanding with sort of 10 to the 51 erg of kinetic energy, and it collides with some sort of pre-expelled material that surrounds the star. It's probably been lost by the star before it exploded. So if this material is sufficiently massive and dense and optically thick, you can actually efficiently convert this kinetic energy into thermal energy in the collision, and this thermal energy diffuses out and is observable to us as radiation. So either of these models can generate the sort of luminosity that we need. So what about the light curve shape? So the common approach is to take these models and use a sort of simple diffusion formalism that's actually been around since the 1980s. So we don't need to know the details of this equation, but this is a generic way to model the luminosity as a function of time of a supernova. It depends on some input luminosity term, so that's either your dipole radiation from your magnetar or the shockwave evolution in a circumstellar collision. And you've got some diffusion timescale that depends primarily on the ejected mass of the material. And with this, we can generate model light curves for a range of different luminosity functions. So here's one of the superluminous supernovae that I showed earlier. And we fit the light curve with both the magnetar model in blue and the interaction model in gray. And the first thing to take away from this plot is that both models do a pretty good job of fitting the light curve. So it's hard to discriminate between them on that basis. If we look at the parameters that go into these models, we find that our best fits tend to have sort of a few up to 20 solar masses of material, similar to what we inferred from the light curve width. And for a magnetar model, you need sort of a few millisecond spin period, which is okay because the fundamental limit for a neutron star spin period is about 1 millisecond, so we're always above that, which is reassuring. And the magnetic field is around 10 to the 13 to 10 to the 15 Gauss. And there are neutron stars in our own galaxy that we know have those kinds of magnetic fields. For the circumstellar interaction model, we tend to find that you need a CSM mass that's comparable to your ejected mass to make this kinetic energy conversion efficient. And that seems like a lot of material to have around a star, but I think that is consistent with what people think may have been injected by Eta Carina in its great eruption in the 1800s. So from these parameters, it's also still difficult to break the degeneracy. Both models can give reasonable light curves for reasonable parameters. So we need to look for other clues. So that's where we kind of were a few years ago. But in the last couple of years, I think there's been some very interesting case studies of individual superluminous supernovae that have really helped to elucidate this question and shine light upon which is the more compatible model with the data. And the first case study I want to talk about is the supernova Gaia 16 APD. So this was discovered by the Gaia satellite that's mapping out 1 billion stars in our own Milky Way. But in the background, it detected a bright blue transient on top of a very faint galaxy. And when we took spectroscopy of this thing, it turned out to actually be one of the closest superluminous supernovae ever discovered. And quickly looking at the optical spectra, we can see that it looks pretty typical. We've got a very blue spectral energy distribution, broad absorption lines from oxygen-2. As it cools down, we lose this blue color, and we see instead cooler lines of, for example, iron-2 and calcium-2. So in the optical, it looks very normal. But what was really exciting about this supernova, apart from its proximity, was its ultraviolet evolution. In fact, this supernova was more than 5 times brighter in the ultraviolet than any other superluminous supernova during about the first month after the explosion. And that's shown most clearly in this lower panel. So we've got in red colors the R-band optical light curve of Gaia 16 APD and 2015 BN, a more normal superluminous supernova. And in blue, we've got the ultraviolet light curves. So you can see that the optical light curves look very similar. But in the UV, Gaia 16 APD starts out much brighter, but eventually, after sort of 10 days after maximum light, it looks extremely similar to the other events. So not only is this UV excess extremely bright, it's also very short-lived. So that was very puzzling initially, and really raises the question, why is this one different from the other superluminous supernovae, and what can we use to learn about the power source based on this unusual property? And the clue to solving this really came from this ultraviolet spectrum from the Hubble Space Telescope. So in the top panel, you can see the black spectrum. This is our optical spectrum from before, and here's the UV spectrum of Gaia 16 APD, compared to, in magenta, a more typical superluminous supernova. So you can see clearly that it's much brighter in the UV with a very steep spectral shape. It indicates a much higher temperature than any other superluminous supernova discovered. But what's also important to note is that the UV absorption lines are much stronger than the absorption lines we saw in the optical. And it's the strength of these absorption lines that allowed us to make some tests that we haven't been able to do before. So let's think a little bit about where these broad absorption lines come from. In the case of a central engine-powered model, most of the energy is deposited inside of a rapidly expanding ball of gas. And in this case, the photons that reach an observer have to diffuse through this expanding material, and thus are subject to absorption from material with a wide range of velocities. So you get a strong Doppler-shifted absorption. In a circumstellar interaction-powered model, you do have photons that are diffusing through the supernova gas, but actually most of the energy is deposited outside of the fast expanding material at the interface where it collides with the slow-moving material. So in this case, you expect most of the photons to escape without being subject to absorption from the very rapidly moving material. And there's a simple way we can sort of model that and try and map that onto our data. So all we did was to take the spectrum of the well-observed normal-looking superluminous supernova, and in the case of a central engine-powered model, we simply assume you got a hotter engine and a higher temperature, the same spectrum, but mapped onto a hotter blackbody continuum. So we divided out the continuum shape and multiplied by a 20,000 Kelvin blackbody. If the high temperature comes from interaction with an external material, instead of reshaping the spectrum, it should add on another component on top of the spectrum. So in this case, we add a blackbody of the same temperature. And what we see is that in the case of a hotter central engine, we do a very good job of matching the observed absorption lines in our unusual supernova. But in the case of adding a blackbody component, the absorption lines here are much too weak. So this is very strong evidence that actually all this excess energy in Gaia 16 APD is being introduced by a central energy source. So this is a really nice test for the central engine model that it seems to pass. So if we think that Gaia 16 APD is powered by a central engine, such as a millisecond magnetar, it makes sense to fit our simple model to the light curve, and that's what we did. So you can see our data points are in black, and our magnetar model is this blue curve that goes really nicely through all of our data points. The other points here are just some other superluminous supernovae for reference. But what was really amazing when we fit this model was that actually the temperature evolution predicted simply from fitting the luminosity predicts a temperature that's higher than any other superluminous supernova right at the time when we see this effect. So from our data, we can see the temperature in this middle plot. The temperature is higher for the black points than any of the other objects here, but it cools and reaches the same temperatures later, and that's exactly what our magnetar-powered model does. So that was really, really nice consistency test, and it turns out that the high temperature here can result simply just from falling in an unusual part of this magnetar parameter space. All it takes is a relatively weak magnetic field with a modest ejected mass to get the hottest superluminous supernova that we've ever seen. So, as I mentioned earlier, this luminosity equation can be decomposed into a power input term and some diffusion term. So the next step was to isolate the power input term for not only Gaia 16 APD, but for all the other superluminous supernovae where we've got data sufficiently high quality to do this. So our magnetar input function depends on a spin period of the neutron star and some magnetic field strength. And not only does the size of this power term depend on that, so does the time scale over which the power decays. So we took all of the magnetar models for these objects. We plot the magnetar input function over time here. And we see that for exactly this regime, up to about 10, 15 days after maximum, Gaia 16 APD has the most powerful central engine. So this is a very nice consistency check that shows exactly why this object was different from all the others, despite still fitting into the same central engine framework that can explain all of these events. So with this, we felt pretty confident that the central engine model is the preferred of the two. compared to the circumstellar interaction model. The other case study I'd like to talk about, just to switch gears slightly, is my favorite superluminous supernova, supernova 2015 BN. So I mentioned before, this is now the best observed superluminous supernova, and you can see here our spectroscopy that covers 30 days before maximum brightness, going to several hundreds of days afterwards. We've also got light curves from the ultraviolet, optical and near infrared, with very dense coverage. So this is really the data set. If you want to test this theory, this is what you got to do it on. So we've already learned a lot from 2015 BN, but to keep things sort of short for today, I just want to talk about one particular feature of the data, and that's the late time evolution. So a supernova is essentially a very hot ball of gas that's expanding. Because it's very hot, it's highly ionized, and because it's ionized, it's quite opaque. You can't see inside of it. But as it expands and cools, this material recombines and becomes transparent. And if you wait for long enough, you can see right through to the center of the ejecta. The problem is that because superluminous supernovae are so much hotter than any other kind of supernova, you've got to wait for a really long time to actually see inside, probably sort of 200 days or more. And because most of these things are very far away, by the time they've been fading for 200 days, they're actually too faint for us to perform these kinds of tests. But that was not the case for 2015 BN. This was both one of the closest and one of the brightest of these kinds of events. So you can see in the bottom panel here, we tracked the evolution of the effective radius of this emitting material. And you can see, indeed, it does initially increase, but about 50 days after maximum brightness, this effective radius starts to decrease as the material recombines. So the gas is still expanding, but the photosphere is receding inside of it. And by 300 to 400 days after maximum brightness, we're actually almost all the way through to the center of this material. And at this point, you can see sort of the density structure, the composition, and all kinds of things that aren't possible to probe at earlier times. So let's have a look at what this sort of looks like. So this panel on the left is the spectrum from early times through to 400 days after peak brightness. And you can see that the blue continuum totally disappears, and these shallow absorption lines are replaced with very strong emission lines. And with these emission lines, we can perform a number of tests. So first of all, we identify the lines as being primarily due to oxygen. We also see calcium and magnesium and iron, the same elements that we earlier saw in absorption. So that does seem to be the bulk of the composition of this material. From the oxygen line ratios, we can infer a temperature of around 5,000 Kelvin, suggests that something is still keeping this material hot even after 400 or 500 days of expansion. And from the luminosity of the strongest oxygen line, 6,300 angstroms, you can actually put constraints on the ejected mass. So to power this line, you need about 10 solar masses of oxygen at that temperature. So these seem to be quite massive and oxygen-dominated explosions. From the width of these lines and the mass, you can infer the kinetic energy, which works out to be about 5 times 10 to the 51 erg. So that's several times higher than a normal supernova explosion. So as well as being unusually bright, these things are also unusually energetic. And the most interesting line in the spectrum is actually this one right here. The oxygen 1 line at 77, 74 angstroms. It's noticeably narrower than any of the other oxygen lines, which suggests it's coming from deeper inside the ejecta. This is a lower velocity, if you will. And this is actually a recombination line that requires an unusually high density compared to the other lines. And what this sort of means, if you put it together, is that you've got some dense shell of material at a low velocity coordinate. And this is actually a robust prediction of central engine-powered models. If you have this overpressure in the center, it sweeps up the innermost material into a thin, dense shell, which would result in lines that look like this. So that was very interesting, but actually, the most exciting thing about this spectrum is shown in this panel here, where we compare it to the spectra at similarly late times of so-called hypernovae. These are the supernovae that are found to occur alongside long gamma ray bursts. And you can see clearly from this plot that the two objects are almost identical. The superluminous supernova and this sample of hypernovae show all the same lines with similar strengths and similar line widths. And this really shows a strong connection between superluminous supernovae and long gamma ray bursts, which has actually been suggested for a while because they occur in similar types of host galaxies. And we know that GRBs are actually engine-powered explosions. Having the same central composition and density structure is almost the smoking gun for an engine-powered model for a superluminous supernova. So with that, and I am out of time, I will finish. And my conclusions are essentially that multiple lines of evidence are now pointing towards an engine-powered model for a superluminous supernova, and these seem to come from stripped and very massive stars. But there are still many outstanding questions. Why do they only occur in dwarf galaxies? Is it because of a low metallicity in their environment? Can we standardize their light curves for cosmology? And I didn't have time to go into it, but many of them have these double-peaked light curves, which I think is the biggest open question for the next year or so. What generates its first short peak. So I'll finish there. Thank you very much.
Thank you very much indeed, Matt. So we have time for a couple of questions. Wait for the microphone.
Yeah, so I was wondering, these are very special supernovae. So in the central engine model, what's so special about the progenitors? Like why does some systems become long gamma ray bursts, some just normal supernovae, and some superluminous supernovae?
Right. So I think this is the question of why do they only occur in dwarf galaxies is the same question.
Yeah,
There's something special about some kinds of stars that allow them to form engines where other stars don't. So the simplest kind of thread that can run through this is that all these core collapse supernovae form neutron stars, and it depends on the spin period and the magnetic field of the neutron star, whether this is a superluminous supernova, if it's got an engine with a long time scale, a gamma ray burst if it's got a very short time scale, or a normal luminosity supernova if the time scale is either extremely long or doesn't form an engine at all. So I think the key ingredient is probably metallicity and how that affects the core rotation, but currently we're quite hazy both on theory and in observations of, we don't have observations of the actual stars in these dwarf galaxies, right? It's an integrated metallicity, so we don't really know which stars are causing this. People also bring in binarity and whether that helps to spin up the core. So I think that's the next question. I think we're now confident that this is roughly what the power source is. Now it's a question of how do you actually get there from stellar evolution.
Yes, yeah, thanks.
Yeah, okay.
Let me ask a question. You said early on, if I understood, that there'd been a technological change that now made surveys not just more sensitive, but unbiased. And I mean, what are you referring to there?
So it's a combination of having roboticized telescopes now that can just take snapshots of the whole sky, and the large CCDs that means you can see the whole sky in a relatively short time scale.
Yeah.
There's also a software side. To actually detect transients is not an easy task. It takes a long time to actually pick out what's new on the sky. So you really need kind of the computing power to look at the image and see what's new, and actually subtracting images from each other to see if new sources kind of pop out. So there's a number of things. Yeah.
Okay. Right.
The real smoking gun for the central engine model would be to see the magnetar. Is there any prospect of that?
Actually, just in the last month or so, the first kind of scenario where you might see it has kind of come out. So there's been a lot of talk about fast radio bursts lately, and there was the first localization of a fast radio burst in a very similar host galaxy to where we find superluminous supernovae within the last month or so. And there's actually a quiescent radio source there that, if that's connected to the fast radio burst and it's in the same type of galaxy, then perhaps the quiescent radio source is actually an old superluminous supernova that we're actually seeing radio emission from the central compact object at this point. So I'm involved in the project now to chase up all the host galaxies of these things and to see if we can detect similar radio sources.
Okay, well, we must move on. Thank you very much indeed, Matt.